Well, hello, ladies and gentlemen out there. Mr. Dorfler here, back for our latest installment in physics. And today we're looking at falling objects. Now, we've been talking about motion in one dimension for basically this entire chapter. Now it's to the point where we're going to be wrapping things up and talk about how this motion in one dimension fits in with objects that are falling. And we're going to be utilizing some very familiar formulas in today's discussion and practice. So, why don't we get started? And it's a very short discussion, but I'm also going to incorporate some more than usual practice problems. Okay, I think I'm gonna do the whole practice F found on page 64. So when we get there, you can be ready and have your book out and follow along and practice alongside us. Okay. So, what are we going to be doing in this section? Well, we're going to be relating the motion of a freely falling body to motion with constant acceleration. We're going to calculate displacement, velocity, and time at various points in the motion of a freely falling object. And then lastly, we're going to compare the motions of different objects in free fall. All right. So, when we are talking about free fall, we are talking about the motion that a body is experiencing, and it's the motion that is only due to the force of gravity acting on that body or that object. We often call this the acceleration due to gravity, free fall acceleration. You might hear those terms just kind of used interchangeably. But one thing you want to note, that's why I have these, asterisks here, is that when objects are in free fall, they are constantly falling faster and faster. And eventually they're going to come to a point what's called terminal velocity, basically where forces start to balance each other out and the body can only continue going at a certain velocity and acceleration because of everything, friction and all that good stuff. But we typically denote gravity with the symbols AG or simply just G on Earth's surface. So if we're talking about other surfaces of other planetary or celestial bodies, we're typically talking about, the general term. But Earth, we typically say G. All right. Oops. So no matter what object we are talking about, free fall acceleration is always going to be the same. And so in this particular book, we're going to use 9.81 meters per second squared. Other books may use 9.8. We're going to be rebels and use a 9.81. On Earth's surface, no matter what point of an object's motion, it's always going to have negative 9.81 meters per second squared. Why is it negative? Well, in the case we're talking about free fall acceleration, the object is falling, and it's falling in a downward direction. Downward is a negative direction in terms of our motion. We've discussed that early on in this chapter. So that's why you'll typically see it with a negative sign in front of it. Now, there will be times throughout this year in this book that you'll see that it's going to be a positive, number, or no signage at all, just simply 9.81 meters per second squared. That's fine, okay? Just roll with it. Now, we think about when a ball moves up in the air. You throw a ball up into the air, okay? As the ball is moving upward, the ball is slowing down in terms of its velocity, but it is still having acceleration acting on it because gravity is constantly acting on that ball. So acceleration will still be negative 9.81 meters per second squared. It's acting in the opposite direction of that ball that has been thrown up into the air. So that is actually what's going to cause the ball to slow down. Now, at the highest point that ball reaches, velocity is going to be zero. But again, the acceleration is still going to be negative 9.81 meters per second squared because gravity is constantly acting on objects that are in air. Now, once that ball goes beyond or stops at that 0 point and then starts falling back down to Earth, the ball is falling, therefore velocity is increasing, and ball is still accelerating at negative 9.81 meters per second squared. Now, when it says that free fall acceleration is the same for all objects, regardless of mass, that's true. We could have a mouse and an elephant decide to go skydiving and that they both jump out of an airplane, they're both going to experience the same free fall acceleration because of gravity is acting on them the same. But you think about that, their masses will be different, but they are all going to experience the same force or same acceleration due to gravity. All right, let's look at a problem here. We've got Jason. Jason decides to hit a volleyball so that it moves with an initial velocity of 6.0 meters per second straight upward. If the volleyball starts from 2.0 meters above the floor, how long will it be in the air before it strikes the floor? Let's process this for a minute, okay? We have Jason, hits a volleyball, has an initial velocity of 6.0 meters per second. The volleyball starts from 2 meters, so just about a little over 6 foot above the ground, or the floor in this case. How long will it be in the air before it strikes the floor? So we've got to have the ball start at 2 meters above the floor. He hits it straight upward with a velocity of 6.0 meters per second. It has to travel back down to the point where it began and continue going until it hits the ground. So we have to think about what our displacement is, because again, we're thinking about displacement. And we also have to think about what other bits of information do we know? Well, we know that it had an initial velocity of 6.0 meters per second upward. But is that all we know? Well, we're talking about objects that are falling. So we know that gravity is impacting them. It has that acceleration value, negative 9.81 meters per second squared. So we need to figure out how long it took the ball to hit the floor once it left Jason's hand until it smacked onto that surface there. All right, so we have to go back to that table where we were given all those formulas, okay? We have to think about, okay, we know we have to solve for time, but we only are given so much information. And so if we kind of give ourselves a visual here where we have, this volleyball starting at 2 meters above the surface, is hit in the upwards direction, okay, at 6.0 meters per second. Eventually, its final location at the end of this scenario will be right here. So what you're going to notice also is over here, we have delta y. If you look underneath the given here, you have delta y instead of delta x. That's okay. The formulas are still going to be the same. All it is talking about is displacement or change in. We're not going horizontally, we're going vertically. So instead of x, we're usually using y. It all works out the same. So what are we trying to figure out here? Well, again, we don't know how fast the ball was traveling or its final velocity was right at the moment that it struck the floor. We also don't know what time it was. So we know that we've got an initial velocity. We know what our acceleration is because of our gravity. And we do know what our displacement is on the y. I'm actually going to go back a slide here. Okay. If I can figure it out. Okay, first I have to erase this. Don't know what just happened there. Okay, sorry about that. That was a little weird. Okay, so back to this. Sorry about that. The displacement we know is negative 2 meters. Why is it negative 2 meters? Well, again, the ball goes up and back down. So at some point, it meets exactly where it started. So its displacement at that point is 0. But the ball continues beyond its starting location to the ground, which we know that distance from the starting location to the ground is 2 meters. So that's why the displacement itself is negative, because it's below where we started. So we're going to use the equation VF squared is equal to VI squared plus 2A delta Y. And we're going to take the formula that has final velocity, initial velocity, acceleration, and time to solve for our second part I guess our main part is how much time did it take for that ball to eventually hit the floor. Okay, so when we're setting up our first equation over here, make sure to remember to take the square root. Get that VF all by itself. No more squares there. Okay, and then rearrange the second formula to solve for delta t. So we got to solve the first formula on the left before we can get into the formula on the right. Okay, and so once we plug in all of our values, we find that we have a final velocity of negative 8.7 meters per second. Again, that negative just is indicative of the direction that it's traveling, down. So now that we've got our final velocity value, we have our initial velocity, we've got acceleration, now we can take that second formula and solve for delta t. So we find after we plug in our numbers, again, this is why it will be in these cases, it's important that we have that negative sign here for our acceleration, that it takes approximately 1.50 seconds for the ball to hit the floor after it is struck by Jason. And it's a reasonable time as discussed in the evaluation part right there. But again, you also want to make sure your signage is correct because time must be a positive value. It cannot be negative. Okay, can't go back in time just yet. All right, so now what we're going to do, that wraps up chapter 2. Now we're going to go to the practice problems. Okay, again, you can follow along on page 64. Okay, let me get my book out here so I can read. Okay, number 1 says a robot probe drops a camera off the rim of a 239 meter high cliff on Mars, where the free fall acceleration is negative 3.7 meters per second squared. A is find the velocity with which the camera hits the ground. Okay, so what do we know for number 1? We know that the object is falling, so our delta y, or displacement, is negative 239 meters because it hits the ground. The cliff is 239 meters high, so we know that the displacement of the camera is going to be downwards. We know that our gravity here is negative 3.7 meters per second squared. And so again, much like our problem here, we don't know what our final velocity is, and we don't know what our delta t is. Okay? So, setting up our first equation for A, we're going to figure out find the velocity with which the camera hits the ground. Vf squared is equal to Vi squared. All right, let me move my keyboard here. Where were we? Plus 2a delta y. And eventually, again, we're going to unsquare this. So we get Vf is equal to plus or minus. That's a terrible square root. Vi squared plus 2a delta y. And so we can go ahead and plug in our numbers here. Our Vi, one thing I did mention over here is what bit of information we do know is our Vi is actually 0 because the camera was at rest before it got knocked off. Okay, so we just go ahead and do that. Pardon me. And so we've got the negative 3.7 meters per second squared multiplied by our displacement of negative 239 meters. And when we plug all that in, we get an answer of negative 42 meters per second. Again, it's negative, or we could say 42 meters per second downward. So, again, downward. If I require you to give me a direction, I'll try to let you know. Otherwise, I mean, like I said, it's good practice if you can pretty much decipher what the direction is. You might want to include that and take out that sign. Part B, though, says we need to find the time required for it to hit the ground. So we're going to use that equation we saw in the practice. Delta t is equal to Vf minus Vi over A. And so our Vf, again, was negative 42 meters per second minus 0 our initial, divided by negative 3.7 meters per second squared. So when we calculate this out, we get 11 seconds. All right, so there's our first problem there. Now, number two, you know what? Number two is pretty similar to number one. Let's move on to number three. Now, I love these types of questions. I love seeing these types of calculations because we are seeing, again, real world stuff. Like these things can actually happen. These things can actually be solved when we're out and about. You know, if you find yourself bored on a weekend, you can go out and do a lot of these experiments yourself. Okay, let's look at number three. A tennis ball is thrown vertically upward with an initial velocity of plus 8.0 meters per second. It's positive because it's throwing up. What will the ball's speed be when it returns to its starting point? Okay, so let's look at this. So we're looking at 3A. Okay, we know that our initial velocity is 8.0, again, a positive 8.0 meters per second. I'm going to try to see if I can't get a little bit better view here. Sorry, it's very sensitive to light changes and angle changes here. Anyway, all right, so our VI is positive 8.0 meters per second. Our acceleration is negative 9.8 meters per second squared. And so, you know, what else are we trying to figure out here? Okay, we are trying to figure out, you know, what will the ball speed be when it returns to its starting point? Okay, so again, that's VF. VF squared is equal to VI squared plus 2A delta Y. All right. So, excuse me. So if we rearrange this, okay, VF squared, start working with this formula, one thing we need to know is our delta Y. Okay, our delta Y. It says in the question, what will the ball's speed be when it returns to its starting point? So, and I don't like the fact that they said speed. I'm going to be really honest. We've been talking about velocity this whole time, and we're still talking about velocity. But the displacement itself, delta Y, will be 0. So here's why. Because that ball goes up from this starting point, but then it comes back down to this original starting point. So its displacement is 0. It is back to where it began. So that means that this is going to be basically eliminated. So we get VF squared equals VI squared. Or VF is going to be equal to plus or minus the square root of VI squared. Well, we know that the initial velocity is positive 8. Okay, so the ball is traveling downwards. So it's going to be essentially equal to negative 8.0 meters per second. Okay, easy peasy. Really no calculations needed for number 3. So again, it's very important that you read your questions thoroughly and think them through. Always document what you know. Back to number 3. This time we're going to be at 3B. Okay. 3B says, how long will the ball take to reach its starting point? Okay, so we already talked about what its final speed would be going at the moment it returned to its starting location, but how long will it take for that to occur? So, again, we're going to be using VF is equal to VI plus A times delta T. Solving for time now, we're going to get delta T is equal to VI minus VF divided by A. All right. So delta t is equal to VI, which again we said was. Oh, I'm sorry. I made a boo-boo. I was looking at the wrong formula, wrong number. Don't do what I did. Don't do what I did. I'm sure some of you are at home going, nope, that's not right. Because as soon as I wrote it and I went to the next step, I'm like, something's off here. Well, we got it fixed, okay? We got it fixed. Anyway, final velocity. It's going to be 0 meters per second. Okay? Next, our initial velocity. Negative 8.0 meters per second divided by negative 9.8 meters per second. All right. So when we calculate this, we get the fact that it will be negative 9.8 meters per second. Oh, shoot. Guys, I got so much writing going on in my hand or in my notebook here. I'm having trouble keeping track of it. So we get delta t is equal to 0.816 seconds. But here's the thing. This measurement is simply for the trip up. Okay? This is for the trip upwards before it started its descent. So if we want to talk about round trip, then you have to multiply this by 2. Okay, again, this is just for the upward trip. And so you multiply by 2 to get your total. You get roughly 1.6 seconds. I think I forgot to mention that when we were doing this, if we just think about the initial travel upwards, then we can only really need to worry about half of our information. That's why your final velocity is 0, because we're not concerned about that in our first initial half of the trip. Okay, so that is 3B, 1.6 seconds. And number 4, calculate the displacement of the volleyball in sample problem F, the one with Jason and the volleyball, when the volleyball's final velocity is 1.1 meters per second upward. Okay, so we're going to use the formulas that we are familiar with, what we know, to solve for our displacement. So y is equal to VF squared minus VI squared divided by 2A. Again, we're using the information from the original practice problem we had. So, again, it says our final velocity is 1.1 meters per second. We're going to take that squared minus 6, which we saw from the problem, meters per second squared, divided by 2 times negative 9.8 meters per second squared. Okay? And so we start getting some values. We have 1.21 meters squared per second squared minus 36.0 meters squared per second squared divided by negative 19.62 meters per second squared. Again, this has a lot of numbers going on. That's why I'm kind of working all through these steps. So eventually we get delta t is equal to negative 34.79 meters squared per second squared divided by negative 19.62 meters per second squared. And the appropriate units are going to cancel out, leaving us with just meters, 1.8 meters. So the volleyball will have traveled, or its displacement will be 1.8 meters at the point that the ball is traveling 1.1 meters per second upward. Okay? So, there you have it, folks. All sorts of different questions for our last practice in Chapter 2. Now, for your homework, you are to do Problem Bank F. And there's only about 8 questions, I believe, in Problem Bank F. However, about 2 or 3 of them I have listed as challenges. Okay, you really got to think through some of these here. Okay, don't think so linearly. Sometimes you have to take a little detour in your thought processes and how to solve them. Okay, so if you have any questions, feel free, if I can get in the camera's point of view. There we go. Feel free to contact me. Why is it so dark? There we go. And I will do my best to email you back in the appropriate amount of time. Oh my goodness. I'm not a left-handed mouse user. So anyway, that's it. That's a wrap for today. It's a wrap for new material for Chapter 2. And I will see you later. Have a good day, ladies and gentlemen.